Welcome, welcome. Unit 4, Lesson 4, Exploring Exponential Models, Growth, and Decay. Yes, this is content that you should have learned in Algebra 1. It is back with a vengeance. And we will do it again in Algebra 2, but we will do it better because Algebra 2 is better, I think. Anyways, it's a good day. The sun is shining. Today is April 1st. I will try to resist the urge to make as many jokes or dad jokes or puns as possible. And we'll do some math, but it snowed yesterday, like 3 inches. It was terrible on March 31st, but I'm told by Mr. Weatherman that it's supposed to be the end of winter. Thank God. It's been 6 months. Let's do some math. All right, let's go over some basic ground rules. An exponential function is a function with a general form y equals a times b to the x. Okay, we've seen this. A, b to the x. Okay, that again, this board is all squiggly. Look at that. Well, let me realign it. All right, there we go, much better. Still squiggly. So it is a, b to the x. And it doesn't even look that much better. Anyways, we've done this with the geometric sequence and series. These were exponential equations, okay? So we're kind of looking right back at that. But please note some important things, okay? First of all, a cannot be 0. What happens if this is 0? 0 times anything is 0. So my exponential goes away. B has to be bigger than 0. But here's the big thing. B can't be 1, okay? B cannot be 1. If B is 1, it doesn't matter what power you have a base 1 to, this becomes 1. 1 times anything, whatever a is, would just be a, and it would be linear. It would not be exponential. What do I mean? Well, if I had 8 times 3, oh, I'm sorry, if my base was 1, if b was 1. 1 to the third, okay? This is just 1. 8 times 1 is 8. It becomes linear, okay? Likewise, if my a was 0, 0 times, let's call this 14 to the x. 0 times anything is 0. Okay, so we don't want a to be 0, and we do not want b to be 1. All right? So those are some ground rules, and please note, and this is the basis behind growth versus decay. If your b value, okay, if you have y equals a b to the x. If your b value is bigger than 1, that represents growth. Because remember, what goes in here, it's really 1 plus whatever your rate is. Okay? If b is between 0 and 1, like 0.5, 0.3, 0.78, whatever, 0.99, then that represents decay. Again, look at that. That means it's 1 minus your r. All right? Basic things about identifying growth or decay in an exponential. All right, so let's take a look at some equations. Let's figure out if they're growth or decay, then figure out the rate of change. When I say rate of change, 1 plus, again, this is off. Let me redo it. Okay, this is number 2. Started out so good. I was so happy. It was sunny. The snow stopped. Okay, give me a second here. Okay, take 2. 1 plus r. The r is my rate of change. That's what I'm looking for. Okay, so is this growth or decay? My b value is bigger than 1, so I know it's growth. Okay, but what is that rate of change? I just take 1 plus r and set it equal to whatever my b value is. I mean, didn't we just say our b value is 1 plus r? I don't really use this. It'll come out. You'll see when we have a decay. I always use 1 plus r to figure out my rate, because if I subtract 1, my rate equals 0.4. That's my growth rate, 0.4. There you go. Good. Now let's look at the next one. This is obviously my b value. It's decay, because that is less than 1. Now if I take 1 plus r, all right, and I set it equal to 0.7. If I subtract 1, my R equals negative 0.3. And that's it. Your rate of decay is, I guess they can really say that rates should really not be negative. If this was a problem, they would say your rate is decaying by 0.3. Okay? Your rate is decaying by 0.3. And maybe that's why they have a minus here. If this was minus, a negative divided by a negative, I want to solve for a positive R. If I make this plus, I would have to make this plus. So my rate would be decaying by 0.3. Now, I still use a plus, and I just realized that, hey, if this is negative, it means decay. Either way is fine. Okay, either way is fine, as long as you can make that connection. If this were a word problem, they might say something is decaying by 0.3. They will not say it's decaying by negative 0.3. Okay, so keep that in mind. The next one. Let's look at our B value. Okay, well, here it is. That is definitely less than 1. That's decay. I'll put a D there for decay. And if I have 1 plus R equals 0.34, and I subtract 1 from both sides, R equals 0.66. Well, that's negative 0.66, so I know my decay is 0.66 positive, because it should always be positive. It's just decaying. This negative sign tells me it's just decaying. All right? Now, for the next two, this is going to be, I don't want to say tricky to understand, but this is something that you've got to get used to doing, okay? If I want to figure out growth or decay, do you see my first three problems that I have here? Do you see the exponent is always, it's just the x? I want to get it so that I just have the x here. I don't want that divided by 5, okay? In order to find out my growth or decay, my b value can only have the x, or the variable as the exponent. Meaning, technically, isn't this 1/5? I'm going to rewrite this. And I'm going to say y equals 3 to the 1/5 power x. I'm literally, in fact, I'll write that slightly better. I'm going to say, I'll put this over here. Y equals 3 to the 1/5 x, okay? It's 1/5 times x. What I'm going to do for my b value is I'm going to actually evaluate my 3 to the 1/5 power, okay? So I'm going to have my calculator, and I'm going to put 3 and raise that to the 1 divided by 5. 1.2457, okay? Well, let's look at our directions here. Round to the nearest hundredth if necessary, okay? And if I look at my calculator, if I round to the hundredth, it's right here where the 4 is, so it'll be 1.25, okay? So this is really saying that's like y equals 1.25 to the x, because this right here in those red parentheses is 1.25. That b value is bigger than 1, so that is growth. Okay, and what is my rate of growth? Well, 1 plus my rate equals my b value. If I subtract 1, my growth rate is 0.25. Okay, so what's the lesson we need to take from this? You need to get your x alone. Any number with that variable needs to be applied to the base as an exponent to figure out your b value. Let me say that one more time. Yeah, highlighter. Any number, this is 1/5, needs to be applied to the base so that the x is alone. 3 to the 1/5, that ends up being 1.25. That is your true b value. You need to get your x alone, all right? And we're going to do the same thing with this last one here. Same thing with this last one. So what do I have? Yep, that's okay. That's just a scroll. Sometimes the board does weird things. Now I'm going to take this -2 and I'm going to apply it to my 4.2. So I've got y equals 4.2 to the -2, and then leave that to the x out here. Okay? And we will do that in our calculator. We will say 4.2 raised to the negative 2. 0.056. Okay, if I round that to the 100th, my 5 will round up. My 5 will round, wow, look at that. We'll round up to a 6. Look at that. Oh, look what I can do. Something new that I've learned. Okay, 5. I like that. So that 5 will round up to a 6. I just tap that. It's better. So now I have the following. I have y equals, is that 0.06? It is. I got so, obsessed with that circle. That's 0.06 to the x. That is definitely less than 1. That is decay. Okay, that's my b value. So 1 plus r equals 0.06. If I subtract 1 from both sides, r equals negative 0.94, which means my rate is decaying by 0.94 or 94%. All right, let's take a look at some modeling using exponential growth and decay. For growth or decay to be exponential, a quantity changed by a fixed percentage each time period. Ooh, okay. Well, let's just go ahead and do this. All right. So what they're saying is, okay, in order to use a fixed percentage, there needs to be a time period, okay, applied to it. And t is the number of time periods that you have. Okay, so keep that in mind. So let's start doing some of these examples and some of these models, i.e. word problems. And we're going to start really basic, okay? For A, let's write the exponential function to model each situation. They're not asking us to solve. They're just asking us to write the model. So for A, the population of 1,236,000 grows at 1.3% per year for T years. Now, one thing that I kind of just perused over, but that I hope you know, is my initial amount, my starting amount is always what goes in front of my parentheses. We had A, B to the X. Okay, my X is now time. My B is 1 plus R or 1 minus R. This A, which goes in front of your B, is always your starting amount. So initial amount is the same thing as your starting amount. It's what you're starting with. The population we have starts at 1,236,000 and grows by 1.3% per year. This is my rate in percent. Something that I always push, because people always do this. When I put numbers into equations, I cannot put percents. There is, and I always tell this to students, I'll give someone $5 if they can find the percent button on this calculator. There is none. Okay, there's no button. If you look at anything in green and blue, any of these things here, there is no percent. How come? Because you need to change your percent to a decimal before it goes into your equation. Let me state that one more time. Need. This is what you need to do. Your rate as a percent needs to change to decimal for your equation. And how do we do that? Slide left 2 times. Slide left 2 times. If you want to write left and then the word 2, then times, so because you don't want to confuse that 2 and x, go right ahead. But if my rate is 1.3%, this goes 1, 2 to the left. Here's the decimal. Any empty spaces get a 0. So my rate is really 0.013. This is my R. This is my A. Let's write our equation. If y equals A times 1 plus your rate to the t, y would equal 1,236,000 say 1 plus 0.013 to the t. Or, if you want, you can combine these. You could say y equals 1,236,000, 1.013 to the t, because this is probably how it would be written on a test. But you should know that this is the same as this. I mean, you should know that addition is simplification. You're good in the parentheses there. Let's try a couple more, B and C. Population of 752,000 decreases. Okay, my rate, first of all, this is the same as saying 4.75%. Now, you might say, oh, look, Visca, there's a decimal there. I can put it in the calculator. Wrong. No. Not only is there a decimal, there's a percent sign. In order to get rid of that, 1, 2, I slide my decimal 2 spots to the left, and I fill any missing loops. So that's 0.0475, okay? And notice it's decreasing. So I'm going to subtract my rate, all right? So y equals my initial value, 752,000, times 1 minus 0.0475 to the t. Or, if I combine those, y equals 752,000 times, and I will get 0.9525 t. And last but not least, a new car that sells for $18,000 depreciates 25% a year for 2 years. Your car was worth initially $18,000. Depreciate means it is decaying. It's going down. If my rate is 25%, okay, the decimal is at the end of 0.25. I move it twice. That's 0.25 without the decimal. Or excuse me, without the percent sign. So let's write this. Y equals 18,000 times 1 minus 0.25 to the t. Or I could combine those and say y equals 18,000 times 0.75 to the t. This means it retains 75%. It loses 25%, so what is it still worth? It's still worth 75% of its value each year. Okay? Bam. This ain't so bad. It's just a trip down memory lane. And you like to reminisce. Yes, you do. I can tell you do. Let's move forward. All right, example 1. Which of the following gives the savings in an account if 250 was invested at an interest rate of 3% per year? Okay, well, I'm looking through this. If you want to guess, we'll start, but the answer should be B. How come? This is your initial amount, A. It's invested at an interest rate of 3%. That means it's going up with an interest rate. Okay, interest is a good thing for you. 3%, there's a decimal, it goes 1, 2, it's 0.03. I'm adding 1 plus 0.03 to my 250 to my time. And of course, if I add those together, this is what I get. Okay? Here you go. Look, if you slide the decimal over once, that's 30%, not 3%. This is taking 1 and adding it to 3. That's not even making it into a decimal. That's leaving the 3 in percent. That is wrong. Okay? The answer is B. If the population of a town is decreasing by 4% per year and started with 12,500 residents, which of the following is a projected population in 10 years? If you want to go ahead and do this, you can pause this because I'm about to do it now. Okay, so the population of town is decreasing by 4%. That means my rate, it's decaying by 0.04. All right, my initial amount was 12,500. So if I were to write this, y would equal 12,500 times 1 minus 0.04 to t. Well, they're asking me, what is the end population? Okay, this is the beginning. We're trying to figure out the end. This is my time. What's my time? 10 years. So T is going to be 10. So 12,500. I can leave this 1 minus 0.4, or I can just call it 0.96 to the 10. I put that in the calculator, and I see what I get. Let's do that. Take 12,500, okay, yeah, times 0.96. In fact, no, if this were a test, you could just say 1 minus 0.04 if you wanted to. Raised to the 10. 8,310. Let's do the same thing, but let's make this 0.96. It should be the same. Okay, keep on going, keep on swimming. 0.96. Okay, and then if I delete, you should get the same thing, and you do. 8,310. So if I were to look at this, well, projected, we're projecting 8,310 people in 10 years because we're losing about 4% a year. Right? That's what happens for towns. That's why it's important to have jobs for people to come move to towns so you can generate income so the government can get taxes to take care of the town, the roads, snow plowing. In upstate New York, snow plowing is big. These are real life situations, people. All right, next one. If you'd like, you guys can try 3, 4, 5, and 6 on your own, and because I'm about to do these right now, and see if you get them right. Okay. Number 3 says, which function represents the value after X years of a new delivery van that costs $25,000 and depreciates 15% each year? Oh, cake. X is my time, so that's going to be my exponent. Okay, X, 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 X. Good. My initial amount is 25,000. It's not negative 15. 25,000, 25,000, 25,000. Depreciates at 15%. That means my rate is 0.15, and depreciate means subtract. So my B value is 1 minus 0.15, which is 0.85. That's going to be my parentheses. Yahtzee. C. Simple. In 2003, the population of the Iberian lynx was 150. In 2004, the population had decreased to 120. If this trend continues and the population is decreasing exponentially, how many I'll be okay. How many librarians will be lynxes? No. How many Iberian lynx will there be in 2017? I like this one because it throws a curveball at you that you may or may not see coming. All right. So in 2003, the population of the Iberian lynx was 150. Okay. So let's call this our starting amount in 2003. All right. In 2004, the population decreased to 120. Okay. So it's subtracted by 30, right? I had 150. I now have 120. Doesn't that mean I got to subtract 30? So this right here, subtracting 30 is going to help me get my rate. If I have 150 and I lost 30 out of that 150, okay, I can reduce that. That's 3 over 15, which actually reduces to 1/5, which is 0.20 in your calculator. All right. So I'm actually decreasing by a rate of 20% or 0.20. Okay, obviously it's decreasing, it's going down. So if my starting amount was 150, taking 1, I'm subtracting 0.20, but how many years? Well, my starting value of lynxes, my quantity, was 150. That was in 2003. They want to know in 2017. That is a distance or time span of 14 years. So I'm going to put 14 right here. Okay, and if I put that in the calculator, Let's do this. Turn this back on. On. 150 times 1 minus 0.2. Yep, that's okay. That's 1 minus 0.20. Raise that to the 14. Wow, man. Look at that. There'll be roughly, 7 links left. Some can argue that, I'm just rounding that up. Some can argue population, you can't add until it becomes 1. You can't have half a links. So depending on the context of the problem, but 7 links left. That sucks. Oh, the final is infamous for asking this type of question. A collector purchases an antique vase. An equation to represent the value A of the antique vase after M months of ownership is A equals 5,000 times 1.24 M over 12. Which of the following statements is not correct? And before we get going, there's a typo here. This should be 1 point. See that right there? It should be 1.02%. Look at that. Let's get that out of the way. And of course, if there's a typo there, probably means that's the important one. It's probably the answer. But let's figure this out, okay? So let's take a look. Just like problems we did earlier, I want to get my variable alone as the exponent. So I want to take my 1/12 and apply that to my base. So it's 1.24 to the 1/12, and now it's per month, okay? So when I evaluate this in my calculator, 1.24 raised to the 1/12. 1.24 raised to the 1, yep, I'll be okay, 12. I hit enter. I'm going to round that. I'm going to round that right here. Oh, yeah, look at me go. It's 1.02 because the number after the 1 is an 8. Okay, so ultimately, I get 5,000 times 1.02 to the M. That is my equation that I'm going to base my answer on. The value of the vase when it was purchased was $5,000. And that is true. It's asking which one is not correct. Yeah, that's my initial amount. That is true. The vase gains approximately 24%. That is not correct at all. That goes up by 0.02. Okay? That means, okay, that goes up by 0.02. Okay? That means it goes up by 2%, not 24. 24 is what it would have went up if we didn't apply the 1/12, but we have to apply the 1/12. This is false. Okay? The vase increase in worth by approximately 1.02% of its value. Yes, this is what it's going up by 1.02% of its value. Okay, that's why that decimal is important. All right. The value of the vase 1 year after it was purchased was $6,200. Okay, if I put 1 year is 12 months. If I put a 12 here for M, let's take 5,000 times 1.02 to 12 months, which is a year. Let's make sure that our answer is B and not D. We said C was true. Okay, let's take 5,000, one more, times 1.02 raised to the 12. That's $6,341. Well, let's purchase. We have 6,300, right? The value of the vase 1 year after purchase was 6,200. You might say, Visca, that's wrong. But remember, we rounded that 1.02. What if we used 5,000? And this is the true base right here. So that's going to be a little bit less because we can't round up anymore. Raise that to the exponent of 12. Look at that. Definitely is $6,200. It's 6,199.999999. That absolutely is $6,200. That's true. Which one is not true? I'm telling you, the number of students that will look at that first one and say, that's true, and circle it, because they don't see the word not, drives me crazy. Number 6, a car is purchased for $30,000. After 1 year, the value of the car is $27,000. Estimate the value of the car after 5 years. Okay. After we did that previous problem, I think it was number 4, we're going to find the rate the same way we did this. Same way. So 30,000, and it went to 27,000. It means it lost 3,000. If I put that over its initial value, that's 1/10, or 0.10, 10%. It loses 10% a year. That's my R. If it started out at 30,000 and 1 minus 0.10, okay, to my time, which is 5 years, I could put that in the calculator. Or I can call that 0.90 if I combine these. Let's figure out what that is. 30,000 times 0.9 raised to 5. Bam. Let's call that, and that's money, right? $17,714.70. That's what it's worth after 5 years. Congratulations, your car is almost a lemon. I'm teasing. So now, if the value of this car after 5 years is $15,000, what is the rate of depreciation? No, that's not the answer. Okay, they're just saying instead of being $17,714.70, if it's $15,000, what is this going to be? Okay, I know this depreciates. I know it's going to start off at 30,000. Okay, yep. It's 1 minus my R. That's what they're asking me to figure out. What is the rate of depreciation after 5 years? And after those 5 years, it's going to be 15,000. We're going to solve for R using opposite math. The first thing I'm going to do is get rid of this 30,000. I'm multiplying my 1 minus R by 30,000. So the opposite of multiplication is division. And that ends up being 0.5. That's a half. 1 minus R to the 5th. Now, I want to get rid of the exponent. So if I'm raising something to the power of 5, okay, I got to put it to the 5th root. Okay, this 5th root and this power of 5 cancel. If you want, you could also raise it to the 1/5 power because they'll cancel. You could do that to both sides as well. 1/5 power is the 5th root. So we're going to take, let's go math. Let's clear this out. Clear. We'll go math. We'll go number 5. We'll put here the 5th root of 0.5. I'm going to have roughly 0.87. Okay, so we got 0.87 equals 1 minus R. Okay, if I subtract 1 from both sides, I get 0.13 negative equals negative R. But our rate, we want it to be positive, right? So if I make this positive, make this positive. We'll say my rate would depreciate at roughly 0.13 in order to make that car worth $15,000 after 5 years. I think we're going to stop here because I don't want to rush this next part. It's not a huge thing, and you know what? I think it's only one more problem left, but I just want to make sure we have enough time to go over it. That will be a small video. So we're going to stop here. This is part 1. Man, been a little bit since I've had to have a part 1 and a part 2, but we're at almost 35 minutes. Let's call it time of death here, and I have a class about to come in anyways. So I will see you very, very soon for Unit 4, Lesson 4, Part 2. All right, take it easy. Stay warm.